Hello everyone, welcome to Passionate Minds. My name is Prabhasha, and today we're going to be looking at grade 11 chemistry, SCH3U, and today's lecture is going to be focusing on chemical equations and chemical reactions as well. Alright, let's get into it. So, chemical equations. A short form method to show and represent chemical reactions is known as a chemical equation. So we're going to be using formulas and symbols when writing out a chemical equation. And the pretty general form is from going from reactants to products. So potential symbols that may be used in a chemical equation are as follows. We have AQ, which is known as the aqueous state, S, which is known as a solid state, L, which is known as a liquid state, G, which is known as a gaseous state, and delta H, which is known as heat. Going back to aqueous, this might be a new term for a lot of you. Aqueous just means something that is soluble in water. So, to give you an example, when you're mixing sugar into your coffee cup, it usually dissolves pretty well, and you don't find many sugar particles inside the coffee at the bottom of the cup. This means that sugar is aqueous. Another example, if you're mixing salt and water, salt dissolves in water, so salt or sodium chloride, NaCl, is also known as aqueous. A word equation example of a chemical equation would be sodium hydroxide plus hydrochloric acid reacts to form sodium chloride and water. A skeleton equation of this word equation is NaOH, which represents sodium hydroxide, plus hydrochloric acid, HCl, reacts to form sodium chloride and water. Now, when we're balancing chemical equations, there are equal numbers of each kind of atom on both sides of the equation for reactants and products. Now, this is due to the law of conservation of mass, which states that matter cannot be created nor destroyed. It can only be transferred from form to form. Alright, to balance, we have to do them in the order of M, P, and OH. We're balancing the metals first, the polyatomic ions second, the nonmetals third, oxygen fourth, and then hydrogen last. And hydrogen and oxygen can be switched. And one more important thing to realize when we're balancing equations is that most of the time they're done in full whole numbers. So I'm going to just quickly go over this before we actually look into the examples, like 1, 2, 3, that sort of thing. However, with oxygen, and it's only with oxygen, you can have numbers that are not whole to balance the equation. And I'm going to be taking a look into this later on in today's lecture. But we can have, for example, 3 halves or 5 halves, 3 over 2, 5 over 2, in place of a whole number when balancing out oxygen. And again, we'll look into this later on. Alright, so looking at the first example we have here, magnesium plus chlorine reacts to form magnesium chloride. Magnesium has a charge of 2 plus, and chlorine gas has a charge of 1 minus. So this is why when we do the crisscross method, chlorine's going to get 2 atoms, magnesium's still going to have the 1. To balance this equation out, we don't need to do anything actually, because chlorine gas is a diatomic molecule, meaning that it has 2 atoms, so we already have chlorine matched up here. We look at magnesium first when looking to balance equations, and we have 1 magnesium on the left side, 1 on the right. That's perfect. 2 chlorine atoms on the left, 2 chlorine on the right. That's perfect as well. Taking a look at the next reaction, aluminum plus hydroxide reacts to form aluminum hydroxide. Alright, now aluminum has a charge of 3 plus, whereas hydroxide has a charge of 1 minus. So when we do the crisscross, we get 3 hydroxide atoms formed as a product, and we still only have 1 aluminum. So aluminum has 1 atom on the left, 1 atom on the right. That's perfect. When looking at hydroxide, it has 3 atoms on the left, so it has to have 3 atoms on the right, so it has to have 3 atoms on the reactant side, which is why we have to write 3 in place of 1, where it was 1 for chlorine. We have to have 3 hydroxide atoms here. Alright, taking a look at another example. Iron 3, which charge of 3 plus, and when it reacts with oxygen, which has a charge of 2 minus, it forms iron 3 oxide. Iron has a charge of 3 plus, whereas oxygen has a charge of 2 minus, so when they crisscross, they don't simplify to an easy number. This means that iron will get 2 atoms because oxygen has a charge of -2, and oxygen is going to get 3 atoms because iron has a charge of 3 plus in this situation. When we're looking to balance this, we have 1 iron on the left side, whereas 2 atoms on the right side. So we normally go and do 2 here and 1 here. But for this situation, we're not going to be looking at reactions where oxygen will have a non-whole number, a fraction. So I decided to make this a bit easier and just use whole numbers for this entire equation. Iron can have, there's 2 atoms of iron here, 1 atom of iron here. But if we do 2 atoms here, this would have to be a fraction. So to get a whole number for oxygen as well, we have to multiply everything by 2. So multiply this entire compound by 2, so we get 4 atoms of iron. This is why we have 4 atoms of iron on the left side. And then we'll have 6 atoms of hydrogen, so we just have to have 3 over here. 3 oxygen atoms, 3 times 2 will give you 6, the same as the right side. Alright, let's take a look at the next reaction. Copper 2 plus reacting with oxygen forms copper 2 oxide. Alright, now there are 2 atoms of oxygen here and only 1 atom of oxygen here. So this means we have to multiply this compound by 2. This is why when we multiply the compound by 2, we need to have another copper atom. This is why copper is going to have 2 atoms. Whereas oxygen already has 2, so we don't need to multiply it any further. Taking a look at the next reaction, we have copper 1 plus nitrogen, which has a charge of 3 minus, forms copper 1 nitride. Now, nitrogen has a charge of 3 minus, so copper is going to have 3 atoms as a product, nitrogen is going to have 1. Because of this, and because nitrogen also has 2 atoms in its diatomic state, because nitrogen is one of the diatomic molecules, as we looked at during the last lecture, we're going to have to multiply this whole compound by 2. And when we multiply it by 2, we get 6 copper atoms. So this is why copper is going to have 6 on the left side, whereas we can keep nitrogen just simple as 1, because it already has 2 atoms. Alright, now taking a look at the final reaction, we have sodium plus oxygen reacts to form sodium oxide. Now, sodium has a charge of 1 plus, oxygen has a charge of 2 minus, so when we crisscross, we get Na2 because oxygen has a charge of 2 minus, and oxygen is going to have 1 atom because sodium has a charge of 1 plus. Again, because we're not looking at fractions yet, and oxygen already has 2 atoms on the left side, we have to multiply this entire thing by 2 to even that out. And then we get 4 sodium atoms, so we can just multiply Na by 4. And before we go to the next slide, just taking a look at the states we have present in these elements and compounds, we can see that pretty much all the elements are going to be solid. Now this stays true to almost every element in the periodic table, save for a couple, like mercury for example, but all the elements here are solid. They should have solid as well. The diatomics, most of them are going to be in the gaseous state, so chlorine, nitrogen, oxygen, that sort of thing. Hydroxide is going to be in an aqueous state, meaning that it's soluble in water. And when we take a look at the compounds that are formed with synthesis, we can see that most of them are solid as well. So all the oxides are going to be solid, so copper oxide, iron 3 oxide, and sodium oxide, whereas compounds without oxygen, for the most part, will be aqueous. And if you are looking to understand more about this, we're going to be taking a look at solubility later on in the course, and the rules will be explained a little bit more as well. All right. Now, the types of chemical reactions. There are 5 main types of chemical reactions that we'll be looking over. We got synthesis, decomposition, combustion, single displacement, and double displacement. Synthesis reactions are reactions when 2 or more elements or compounds combine to form one new compound. The general structure is element A or compound A plus element B or compound B combined to form compound AB. All the examples that I showed you in the previous slides are examples of synthesis reactions. So element A, magnesium, plus element B, chlorine, combined to form compound AB, magnesium chloride. Again, element A, aluminum, plus element B, or compound B, hydroxide, combined to form compound AB, aluminum hydroxide. Element A plus element B combined to form compound AB, element A, element B, compound AB, element A, element B, compound AB, and one more time, element A, element B, compound AB. These are all examples of synthesis reactions. Now, decomposition reactions are a bit different. They're basically the opposite. These reactions are where one compound gets broken down into 2 or more smaller compounds and elements. So, compound AB gets broken down into compound or element A and compound or element B. Looking at a couple examples of this, we can look at the decomposition of water, also known as hydrolysis. With water, when it gets broken down, it breaks down into hydrogen gas and oxygen gas. To balance this equation out, we have to have 2 compounds of water, 2 hydrogen molecules, whereas we only need 1 oxygen because there's 2 here, so we only need 1 of O2. The decomposition of calcium carbonate breaks down into calcium oxide and carbon dioxide. In this situation, the equation is already balanced because we have 1 calcium on the left side, 1 on the right, 1 carbon on the left, 1 carbon on the right, 3 oxygens on the left, 1 with oxide, 2 with dioxide. As you can see, a larger compound is broken down into smaller compounds or elements in the case above. Now, taking a look at the breakdown of nickel oxide breaks down into nickel and oxygen. To balance this equation out, since nickel has a charge of 3 plus and oxygen has a charge of 2 minus, we have to balance this equation out. So we need 4 nickel oxides because, again, we're not dealing with fractions yet for oxygen. So we need 4 nickels. And since we have 6 oxygen, we need 3 oxygen molecules on the right. All right, taking a look at the last example, potassium permanganate, breaking down into potassium oxide, manganese dioxide, and oxygen gas. Now I'm using fractions here just to illustrate. For this one, we have 2 potassium oxides on the right, so we need 2 on the left as well. So now we have 2 manganese on the left, we need 2 on the right. So we have 4 oxygens, 5 with the oxide, and since we have 8 oxygens on the left, we need 8 on the right. We already have 5 here, so this means oxygen, which already has 2, we need to multiply by 1.5 or 3 halves to get 8. Alright, now taking a look at combustion reactions. Combustion reactions are where the reaction has a fuel present. This is normally a hydrocarbon, which reacts with oxygen, producing oxides, water, and potentially solid carbon as well. Now, these reactions can be complete, where all of the reactants are used up and it only produces carbon dioxide and water vapor, or incomplete, which means that there's not enough oxygen and carbon monoxide will form and potentially solid carbon as well. Taking a look at some of the examples we have here, again, a hydrocarbon, if you don't already know, is a compound which has carbon and hydrogen. Carbon and hydrogen, that's it. This one right here, CH4, is more commonly known as methane. So when methane reacts with oxygen, and when there's enough oxygen to fully combust, we get carbon dioxide and water. Balancing this out, we have one carbon on the left, one carbon on the right, that's good. 4 hydrogens on the left, that means we're going to have to multiply water by 2 to get 4 on the right. And since we have 2 oxygens here and another 2 here to make 4, we have to multiply O2 by 2 as well. Taking a look at the next one, again, methane plus oxygen, and this one is incomplete. I guess we didn't have enough oxygen to fully combust. They combine to form carbon monoxide, CO, water, and carbon in a solid state. Within this reaction, we take a look at the carbons. So we have 4 carbons on the left. We want to have 4 on the right as well. So we multiply carbon monoxide by 2. We multiply carbon by 2. Now we take a look at the hydrogens. We have 16 on the left, so we have to have 16 on the right. Water is the only molecule that has any hydrogens, so we multiply this by 8. When taking a look at oxygen, we have 8 oxygens here, another 2 here, so we need 10 on the left. Just multiply O2 by 5, we get 10. There we go. Now, taking a look at the third combustion reaction, this is also incomplete, but we don't have solid carbon present. C4 plus O2 combine to form carbon monoxide and water. That's it. In this reaction, we're going to be needing 2 carbons on the left, so 2 on the right as well. We have 8 hydrogens present here, so we have to multiply water by 4 to get 8 hydrogens. And we have 2 oxygens in carbon monoxide, 4 oxygens in water, which means we're going to need 6 here. So just multiplying O2 by 3. Finally, we're going to take a look at a different compound, ethane, not methane. Ethane is characterized by two carbons. It's a 2-carbon compound. And ethane plus oxygen combine to form carbon dioxide and water. In this compound, we had enough oxygen to fully react, and we're going to be using fractions here. C2H6, or ethane, is only going to need 1. So on the right side, we need 2 carbons. So after that, we take a look at the hydrogens. We have 6 hydrogens on the left side, so we're going to need 3 molecules of water to have 6 on the right side. Taking a look at the oxygens, we have 3 in water, 4 in carbon monoxide, so we're going to have 7 oxygens present on the left side, which means we have to multiply O2 by 7 halves to get 7. Alright, now taking a look at single displacement reactions. These are reactions within a compound where one element is displaced by another element. Now these reactions typically occur with metals and halogens, and the more reactive elements can be replacing the less reactive element, otherwise the reaction cannot occur. So the general structure is element A plus compound BC combine to form compound AC and element B. We're going to be using the activity series of metals and nonmetals when looking at single displacement reactions to see exactly if a reaction will occur or won't. So looking at the activity series, the higher placed elements are going to be the more reactive ones. So lithium is the most reactive, then potassium, barium, calcium, sodium, so on and so forth. And then we see hydrogen here as well. Hydrogen's low place on the activity series indicates that it's not very reactive. Even though it is a nonmetal, it's placed in the activity series of metals just to indicate which ones are more reactive than hydrogen and which ones are less reactive. So copper, silver, mercury, platinum, and gold are very unreactive as they're less reactive than hydrogen. And the elements above it are going to be more reactive. Taking a look at the nonmetals as well, we can see that fluorine, chlorine, bromine, and iodine are the series of nonmetals that we have. Fluorine is going to be the most reactive, then chlorine, then bromine, then iodine. In a reaction where we say element A is, for example, cobalt, and element B in compound BC is lower than cobalt, element A is going to replace element B in compound BC and then form compound AC. To use cobalt as again, if cobalt is element A, say copper is element B, cobalt is going to replace copper and then form compound AC. Same goes for nonmetals. If we have fluorine as element A and bromine as element B, fluorine is going to replace bromine to form compound AC. Now we take a look at some examples. We can see here in iron plus copper sulfate combined to form copper and iron sulfate. Iron is, let's take a look, right here on the activity series, but copper is a lot lower than iron, which means that iron's more reactive and it will replace copper within this single displacement. This reaction is already balanced, so we don't need to add any whole numbers. But as we can see, since copper is lower than iron within the activity series, it's going to have to be replaced. Now, we take a look at another example. Copper plus sodium bromide. Sodium is pretty high on the activity series, whereas copper is really low. This means that no reaction can occur because of the placement of copper relative to sodium. This is why there's no reaction occurring here. We take a look at copper again. Copper plus silver nitrate, and silver is lower than copper, so a reaction can occur. Copper nitrate forms and silver solid is formed as well as a byproduct, but since silver is lower than copper, copper can displace it within this reaction. Alright, and one more example with metals, we have zinc and hydrochloric acid. Zinc is right here on the activity series, but hydrogen is a lot lower. Because of this, zinc can replace hydrogen and form zinc chloride and hydrogen gas as a byproduct. Now taking a look at non-metal reactions, chlorine gas plus sodium bromide combine to form sodium chloride and bromine. Chlorine is higher than bromine on the activity series, so chlorine is going to be able to replace bromine, displace it. We do have to balance this out because we have two bromines on the left, two chlorines on the right, so we have to multiply NaBr by 2 and NaCl by 2 as well. Same goes for chlorine gas plus potassium bromide combined to form potassium chloride and bromine gas. Again, in these situations, we don't look at the metal, we look at the non-metal because we have a non-metal as element A. Again, chlorine's higher than bromine, so chlorine's going to be able to displace it. We do have to multiply potassium bromide and potassium chloride by 2 to balance out the chlorine. To balance out the chlorine on the left and the bromine on the right. Taking a look at another reaction, fluorine gas plus sodium iodide combine to form sodium fluoride and iodide gas. Fluorine is very high on the activity series, whereas iodide is very low. So fluorine is going to be able to displace iodide to form sodium fluoride. We have to balance these out, and we get 2 sodium iodides and 2 sodium fluorides. Finally, taking a look at bromine gas and potassium chloride, bromine is lower than chlorine, so no reaction can occur. Alright. Now, double displacement reactions. These reactions are where the cations, the positive ions, are going to be exchanged between the two compounds. These are normally the metals, but we can also have the non-metals, or for example hydrogen as well, being exchanged. And one of the compounds may form a precipitate. We're going to be using the solubility rules to confirm this later on within the course. And the general structure is compound AB plus compound CD combined to form compound AC and compound BD. Taking a look at these reactions, we have sodium hydroxide plus calcium bromide combined to form sodium bromide and calcium hydroxide. Sodium replaces calcium in calcium bromide, and calcium replaces sodium in sodium hydroxide. Balancing these reactions out, we need 2 sodium bromides because there's 2 bromines here, and because of that we need 2 sodium hydroxides because we have 2 NAs, and then we need 2 hydroxides, and since we already have that, the reaction is balanced. Taking a look at the next reaction, silver nitrate plus sodium chloride combine to form sodium nitrate and silver chloride. Silver replaces sodium in sodium chloride, sodium replaces silver in silver nitrate, and this forms sodium nitrate, NaNO3, and AgCl or silver chloride. The next reaction, lead 2 nitrate plus sodium sulfate combine to form sodium nitrate and lead 2 sulfate. Lead replaces sodium and sodium replaces lead in the respective compounds. To balance this reaction out, we do need 2 sodium nitrates because we have 2 nitrates on the left side, and we need 2 sodiums, but since we already have that with Na2SO4, the reaction is completely balanced. Now, the next reaction, copper sulfate plus hydrogen sulfide, they combine to form sulfuric acid and copper 2 sulfide. Now, within this one, copper replaces hydrogen in H2S, and hydrogen replaces copper in CuSO4. This reaction is already balanced out, so we don't need to add any whole numbers. And take a look at the final reaction. Barium chloride plus copper 2 sulfate combine to form barium sulfate plus copper 2 chloride. Barium replaces copper in copper sulfate, copper replaces barium in barium chloride, and this reaction is already balanced out as well. Finally, we're going to be looking at neutralization reactions. Now, these are just reactions where an acid and a base combine to form water and an ionic compound. They are a subtype of a double displacement reaction, as both of the cations are going to be substituted between each other. And one very popular example of this is sodium hydroxide plus hydrochloric acid combined to form sodium chloride and water. Sodium chloride is a salt, sodium hydroxide is a base, hydrochloric acid, as in its name, is an acid, and water is water. And that sums it up for today's lecture. Tune in for the next lecture where we're going to be looking at Unit 3 and focusing more on calculations, moles, and that sort of thing. Thanks, guys.